Hey again, folks. Our last problem was pretty simple and only involved work, so let's try a problem that uses both concepts of work and kinetic energy. Here we want to apply a completely horizontal constant force on this crate in order to move it up the ramp. As it moves, the crate will experience the resistive effect of friction. Our goal is to figure out the net work that's done on the crate and then use that to figure out how long it takes to push it all the way up there. Let's get started on a free body diagram. The first thing I've done here is set up our coordinate axes so that the x direction is parallel to the ramp and the y direction is perpendicular. We've seen in quite a few problems now that this makes things quite a lot easier to deal with. Let's get some vectors on the page next. The first one will be the crate's weight, pointing straight down, followed by the normal force, pointing in the plus y direction. In the x direction, we need to include our applied horizontal force and kinetic friction, which points in the direction opposite of the crate's motion. There's no other forces acting here, so we can insert our angle for the weight and applied force vectors, and then break both of those down into their components. And that's it for the free body diagram. We aren't calculating an acceleration here, so we can skip the sum of forces step and go directly into calculating the work of each vector. The x component of the weight points in the negative direction and acts over the entire length of the ramp, so the work done there will be negative. The y component doesn't do any work since the crate isn't displaced in the vertical direction relative to the ramp. Moving on to our applied force, the x component there is positive and also acts over the length of the ramp, resulting in this positive value. Similar to the y component of the weight, the y component of our applied force doesn't do anything here either, for the same reason. The same goes for the normal force. Let's not forget about the kinetic friction. That's pretty obviously negative, and of course, it resists the movement along the entire length of the ramp, giving us another negative number. When we sum these three values on the right together, we get the net work done on the crate to push it up to the top of the ramp. And part A is done. We'll end up using this to answer part B next. To do that, we have to review a very important theorem found in this chapter called the work-energy theorem. This says that the net work done on an object is equal to its change in kinetic energy. Since the factor of 1/2 and the mass of the object doesn't change when it starts to move, well, we can factor those two pieces out and write the theorem in a neater form, like this. If we use this theorem, we can simplify it a little bit for our situation here. Recall that the crate was not moving before we started pushing on it, so that means that the initial velocity, this term, will be 0, and our work-energy theorem expression just reduces to this. What we want to do is algebraically solve for the final velocity term. So we'll multiply by 2 and divide both sides by the mass, then take the square root. When you plug in all the numbers, you'll end up with the following velocity. But what we want is the time it takes to get to the top, not how fast it's moving once it gets there. So is this result even useful? Well, actually, yes, it is. We can use that final speed in conjunction with the following kinematic equation to solve for the time. Multiply by 2, then divide by the velocity sum in the parentheses on both sides, like this. Remember, our initial velocity was 0, so really, we're taking 2 times the length of the ramp divided by the final velocity that we just solved for, like this. And when you plug all that in, you get the following time. With that done, we have the solution to part B, and everything is finished. Hopefully this helped. Take care.